Hello and welcome to all students. In this lecture, we will learn about Euclidean space, and here we will discuss about the point, length, or norm of a vector. So see here, norm or length of a vector. So first of all, we take one example to uh, how to find length or norm of a vector. So let us consider the two-dimensional space R2, and in this space we draw x-axis, y-axis. This is our R2 plane, both are perpendicular, and here we draw a vector 4, 3. Suppose 4, 3, where is the position of that vector 4, 3? So 4 is on the x-axis and 3 is on the y-axis. So here is the position of the vector 4, 3. Okay, so this is vector 4, 3. So this vector 4, 3 we can write as a addition of two vectors, and first vector we write it as a, so these two vectors are, we draw here, first vector is 1, 2 and second vector is 3, 1. So we observe that the vector 4, 3 is the addition of vector 1, 2 and 3, 1. Okay, so if we complete the parallelogram suspended by vector 1, 2 and 3, 1, so we observe that the vector 4, 3 is the long diagonal of a parallelogram suspended by the vector 1, 2 and vector 3, 1. Therefore, this vector 4, 3 geometrically it is a long diagonal of a parallelogram suspended by these two vectors, and it is the vector 4, 3 is the addition of these two vectors. Okay, so that's it. Now the same vector 4, 3 we can represent as the addition of another two vectors. So what are these two vectors? So first vector is 0, 3 and the second vector is 4, 0. So addition of these two vectors 0, 3 and 4, 0 is 4, 3. So if we complete the parallelogram suspended by this vector 0, 3 and vector 4, 0, then we observe that, okay, so here we have completed the parallelogram suspended by this vector 0, 3 and vector 4, 0. Now we observe that this parallelogram is nothing but a rectangle suspended by these two vectors, or we can say it is a parallelogram also, no problem. Okay, so now observe that the vector 4, 3 is again a a diagonal of a parallelogram suspended by this green vector and this yellow vector. So this is the way of representing. So one vector we can represent as an addition of pairs of uh, vectors. So these pairs not unique. The pair may not be unique. Okay, so different pair of vectors. Now our main target is to find the length of vector 4, 3. So length of vector 4, 3 is nothing but the length of this line segment, or we can say the vector starting from 0 to this point, the length of this vector. Okay, so this length here we called it as a norm. Okay, length of vector we call it as a norm. Okay, so length of this vector. So now we observe here the right angle triangle from this origin right angle triangle starts from this origin to point 4 comma 0 to point 4 comma 3 to point origin. So in this right angle triangle, the vector 4 comma 3 is a hypotenuse of that right angle triangle by, and now I want to find the length of this hypotenuse. So we use Pythagoras theorem to find the length of this hypotenuse. So by Pythagoras theorem, the length of this hypotenuse is equal to the square root of length of square of length of this vector plus square of length of this side, but the length of this side is same as the length of this vector. Okay, so come here and see the norm means length of. So this is the notation for length of a vector, or we can say norm of a vector. So length of a vector, now we call it is length of vector. So length of vector 4 comma 3 is equal to, by Pythagoras theorem, it is square root of length of vector 4 0 plus length of line segment this, but the length of line segment this is same as length of vector 0 3 because they are opposite sides of a rectangle. Okay, so length of this green line segment is nothing but the length of vector 0 3 and its square. So this is Pythagoras theorem. So norm of vector or length of vector 4 comma 3 is equal to square root of 4 square. So length of this vector is 4 square plus length of vector 0 3 0 comma 3, the length of this vector is 3 and we have 3 square. So if we calculate, do the calculation of all these things, it becomes 16, it becomes 9, 16 plus 9 is 25, and 25 square root 10 to 5 is 5. The length of this vector is 5. Okay, so main point we observe here is this step. Main point we observe here is this step. The norm or length of vector 4 comma 3 is equal to square root of addition of squares of its component. See here, the norm of the vector 4 comma 3 is equal to square root of addition of squares of components of this vector. That is the way of finding the norm of a vector in R2, and we generalize this in Rn. So see the next slide. We define the norm or length of a vector in Rn. So let x is equal to x1 comma x2 comma dot 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 comma xn be any vector in Rn. Then the norm of a vector x is denoted by this notation. We call it is norm of x, and is defined as norm of x is equal to, as we have seen already in the previous slide, norm of x is equal to square root of addition of squares of components of vector x. These are the components of vector x, and this is the addition of squares of square root of addition of squares of component of vector x. So norm of x is equal to square root of x1 square plus x2 square plus dot 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 plus xn square. So this is the definition of norm of a vector in Rn. So we note some points here. So first point is norm of a vector geometrically represents length of that vector. So as we have seen earlier, the norm is nothing but the length of that vector. And so this bracketed quantity, as we have seen in the previous lecture, this bracketed quantity is nothing but the dot product of x with x. So norm of x is equal to square root of dot product with itself. So this is another definition we can say for the norm of a vector. Norm of vector x is equal to square root of inner product of x with itself. We can say like this also. The norm of zero vector is always 0, and the norm of unit vector is always equal to 1, because norm represents length of that vector. The length of zero vector is 0, length of unit vector is 1. Okay, now consider some examples based on the norm of a vector, or from onward we can say the length of a vector, or say norm of a vector, no problem. So but remember, norm is nothing but the length. Norm of a vector is nothing but the length of that vector. Okay, that is if x is equal to 4 comma 2 is a vector in Rn, then the norm of a vector x is norm of x is equal to square root of. So by definition, how to find norm of vector x? It is equal to square root of addition of squares of its components. Addition of squares of its components. Okay, so 4 square plus 2 square, it is equal to square root of 4 square is 16 plus 2 square is 4, and it is equal to square root of 16 plus 4 is 20. Now let us take the example number 2. If x is equal to vector minus 2 comma 5 comma 3 is a vector in R3, then the norm of vector x is given by like this. Norm of vector x is equal to square root of minus 2 square plus 5 square plus 3 square minus 2 square is 4, 5 square is 25, 3 square is 9, and the addition of these three numbers is 38. So norm of vector x is equal to square root of 38. So these are the some examples of examples on the norm of vectors. Now see some properties of norm of a vector. So let us state the statement. Let x is equal to x1 comma x2 comma dot 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 xn, and y equal to y1 comma y2 comma dot 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 yn be any two vectors in Rn, and alpha belongs to R be any scalar. Then first property is norm of vector x is equal to norm of vector minus x. So geometrically this property says that the norm of a vector, or length of a vector, and length of its negative vector is same. The length of a vector and length of its negative vector is same. Now second property is norm of vector alpha x is same as modulus of alpha times the norm of vector x. Third property is norm of vector x is always greater or equal 0. The meaning of this property is the length of any vector is always non-negative. The length of any vector is always non-negative, or length of any vector is always 0 or greater than 0. And the fourth property is norm of vector x is equal to 0 if and only if x is 0 comma 0 comma dot 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 0. Or geometrically we can say that norm of or length of vector x is 0 if and only if that vector x is a 0 vector. Only 0 vector has length 0. Okay, so fifth property is norm of x plus y is less than or equal to norm of x plus norm of y. This property is also known as triangle inequality. So this property, in other words, we can state like this: the length of one side of a triangle is always less than or equal to the addition of length of lengths of other two sides of a triangle. So that is the triangle inequality. And let us see the proof of these properties one by one. Property number one. So property number one is norm of x is equal to norm of minus x. Let us prove this property. Proof, consider. So as we know that vector x is uh, vector with n components, x1 comma x2 comma dot 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 comma xn, and what will be the vector minus x means negative of vector x. Negative of vector x is minus x is equal to minus x1 comma minus x2 comma dot 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 comma minus xn. This is the negative of vector x. Now let us take the norm of or length of this negative vector x. Length of or norm of minus x is equal to, by definition, it is square root of addition of squares of components of vector minus x. So into is equal to square root of minus x1 square plus minus x2 square plus dot 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 plus minus xn square, and it is equal to square root of minus x1 square is x1 square plus minus x2 square is x2 square plus dot 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 plus minus xn square is xn square. But this is nothing but the definition of norm of x. Okay, so thus we have proved the norm of minus x, the norm of negative of vector x is same as norm of vector x, means the length of vector and length of its negative vector is same. Now consider the second property. In second property says that the norm of alpha x, vector alpha x, the norm of vector alpha x is equal to modulus of alpha times the norm of vector x. So let us prove this property. We know that alpha x is a scalar multiplication, is a vector, which is a vector, or we can say it is a scalar multiplication of x with alpha, and it is a vector having n components. First component is alpha x1, second component is alpha x2 comma dot 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 comma nth component is alpha xn. Now let us take the norm of vector alpha x, and it is equal to square root of the addition of squares of components of alpha x. So alpha x1, alpha x2, alpha xn, these are the components of vector alpha x. So we make a square and add them. So alpha x1 square plus alpha x2 square plus dot 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 plus alpha xn square, it is equal to square root of alpha square x1 square plus alpha square x2 square plus dot 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 plus alpha square xn square, and it is equal to square root of, so from these terms we take alpha square common, so into bracket it remains x1 square plus x2 square plus dot 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 plus xn square, and it is equal to if I take this alpha square outside of the square root, then it becomes a plus or minus alpha, and it is a square root of into square root of x1 square plus x2 square plus dot 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 plus xn square, and it is equal to, this is plus or minus alpha is nothing but modulus of alpha, mod function mod alpha, and into this square root is nothing but norm of vector x, and thus we have proved the second property. Now consider third property, norm of x is greater or equal 0, or geometrically we can say that norm of any vector is non-negative, or we can say that norm of any vector is 0 or greater than 0, or length of any vector is 0 or greater than 0. So let us prove this property, as we know that square of any real number is always non-negative. Therefore xi square is greater or equal 0 for all I equal to 1 to n. So this implies x1 square plus addition of squares, x1 square plus x2 square plus dot dot plus xn square is also non-negative, and if we take a square root on both sides, then square root of x1 square plus x2 square plus dot 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 plus xn square is greater or equal 0, and this implies norm of vector x is greater or equal 0. Thus we have proved this third property also. Okay, these properties are very simple. Let us take the property number 4. Property number 4 says that norm of a vector x is equal to 0 if and only if that vector x is a 0 vector. So it is very simple. Here, suppose consider the norm of vector x is equal to 0. So by definition, what is the norm of vector x? So norm of vector x is equal to 0 if and only if we have a square root of x1 square plus x2 square plus dot 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 plus xn square equal to 0, because norm of vector x is nothing but square root of summation of xi squares and is equal to 0, and this quantity will be 0 if and only if the quantity inside the square root is 0, means if and only if x1 square plus x2 square plus dot 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 plus xn square is equal to 0, and this addition will be 0 if and only if this is the addition of squares, and this addition is 0 if and only if all terms are 0, means all xi squares are 0 for I is equal to 1 to n, and xi squares are 0 if and only if xi is 0 for all I equal to 1 to n, and if all xi's are 0, then x must be a 0 vector. So thus we have proved that the norm of vector x is equal to 0 if and only if the vector x is a 0 vector. Vector x is a 0 vector. Now consider the last property of norm of a vector. So this property is also known as triangle inequality. Norm of x plus y is less than or equal to norm of x plus norm of y. Proof: we know that vector x plus y is a vector in Rn with vector in Rn having n components, and its components are x1 plus y1 comma x2 plus y2 comma dot 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 comma xn plus yn. Therefore if I take a norm of vector x plus y, and norm of this vector is equal to square root of x1 plus y1 square plus x2 plus y2 square plus dot 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 xn plus yn square, and take a square on both sides, and this will implies norm of x plus y square is equal to, just we remove the square root on the right hand side, and now consider the last term on the previous slide. Okay, so what is this? It is norm of square of norm of x plus y is equal to it is x1 plus y1 square plus x2 plus y2 square plus dot 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 plus xn plus yn square. So we expand each of these brackets, and if we expand all these brackets, then we get second step. So what is the expansion of bracket x1 plus y1 square? So here I have written the expansion x1 square plus 2 times x1 y1 plus y1 square. So similarly we can expand these remaining brackets. In third step we collect the xi squares together. Then after that we collect the y squares together, and plus we collect the product terms together. Okay, so this bracket containing xi squares, so this color is magenta color. So bracket with color magenta is nothing but norm of x square, and the bracket with color blue means y1 square plus y2 square plus dollar plus y square. This addition of squares is nothing but norm of y square, norm of vector y, and plus now the remaining from these in this bracket we take 2 common, and inside the bracket it is left x1 plus y1 plus x2 plus y2 plus dot 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 plus xn plus yn. So norm of x square keep as it is, norm of y square keep as it is, plus 2 times. So this bracketed quantity is nothing but inner product of x with y. And in the second step, first term, second term will keep as it is, 2 will keep as it is, but instead of this real number x dot y, we will put its modulus. And we know that modulus is always greater than or equal to its real number. Modulus of a real number is always greater than or equal to a real number. So this modulus is greater than or equal to this real number. Therefore, we put this greater equal sign here. In the next step, we again put norm of x square as it is, norm of y square as it is, plus signs as it is, 2 as it is. But here, modulus of norm of x dot y is less than or equal to norm of x into norm of y. So this is the result we will prove afterwards. Okay, so keep in mind the modulus of x dot y is less than or equal to norm of x into norm of y. Okay, and now, so that's why this step is less than or equal to this step. So this step is bigger than the previous step. Okay, so this step is bigger. Now again we see this step or these terms are nothing but the expansion of this bracket into bracket norm of x plus norm of y square. The expansion of this bracket is exactly this term. Therefore, we put here equal to sign, because this term, this step is equal to this step. Okay. Now finally, what we have is thus norm of x plus y square is less than or equal to norm of x plus norm of y bracket square, and take a square root, and we get the required thing, norm of x plus y is less than or equal to norm of x plus norm of y. So this is very important uh, property, and the proof is also very quite easy, not so hard. Okay, and based on this topic we have some examples for practice. We You solve these examples at home, try to solve these examples. Okay, for this take a screenshot for this take a screenshot of this slide, and we end our lecture here. uh, okay, thank you.